Okay, Aaron, you sent me a couple questions about mastering chemistry. Okay, I replied to one of them. This is the mechanism for epoxidation with MMPP. I haven't actually tried this out on mastering, but this is how it would work. Okay, so the alkene goes to the oxygen. And then this bond goes here, and then this bond goes up and grabs the H, and then this bond attacks the other side of the carbon. Okay, so we're going to continue with chapter 11. Okay, let me get that pulled up here. Canvas.
Dr. Trump?
Yes.
Can you let Isabel in? She's in the waiting room.
Okay. Yeah. All right, hold on. Okay, here we go. Yep, there we go. Wait for PowerPoint to load. There we go. Because last time we had just introduced the introductory couple of slides here. Right, in this chapter, we're looking at starting with alcohols and converting them into other functional groups. Okay, and here is an overview of the types of reactions that we'll be looking at. Okay, these include dehydration, the E1 reaction. Okay, we've looked at that already. We've looked at substitution by halogens. Okay, most of these are new. We'll look at oxidation, reduction, esterification, tosylation, and then we'll also look at forming ethers. Okay, first we'll look at oxidation. In inorganic chemistry, oxidation is the loss of electrons. Reduction is the gain of electrons. Okay, remember the mnemonic oil rig. Oxidation is loss, reduction is gain of electrons. Okay, there are clues that we can look for in organic reactions. For example, if we have a gain of oxygen, 2 oxygens, or 2 halogens, or loss of 2 hydrogens, then it's an oxidation. By reduction, we can recognize by gain of hydrogen or hydride, loss of O or O2, and loss of X2. Okay, if we gain or lose a proton or water or OH, HX, or any of those, that's neither an oxidation nor a reduction. Okay, so these are the various stages of oxidation. Right, an alkane, specifically the terminal carbon of an alkane. This is its fully reduced state. Okay, the first step is oxidation of an alkane to a primary alcohol, then an aldehyde, then a carboxylic acid. Okay, if we compare the alkane with the primary alcohol, we've gained an oxygen. Okay, if we compare the primary alcohol with the aldehyde, right, notice we've lost 2 hydrogens. Okay, we've lost a hydrogen here and a hydrogen off the oxygen. And going from an aldehyde to a carboxylic acid, we've gained an oxygen. Okay, when an alkane is oxidized to a secondary alcohol, okay, again, that's a gain of an oxygen, so that's an oxidation. And from a going from secondary alcohol to a ketone, we're losing 2 hydrogens. Okay, and then the ketone is not easily oxidized further. Okay, to oxidize a ketone, you actually have to break a carbon-carbon bond, which is more difficult than breaking a CH bond. Okay, a tertiary alcohol doesn't usually undergo further oxidation. Okay, that's where it stops. Then you'd have to break. Okay. All right. Right, so a secondary alcohol gets transformed into a ketone. Okay, some of the ways of doing that. Okay, I think someone needs to mute their microphone. Okay, secondary alcohol becomes a ketone, and there are various ways we can do this. One way is to use chromium reagents, high valent chromium reagents, such as sodium dichromate or chromic acid. When you combine sodium dichromate with sulfuric acid, the active agent is probably chromic acid. There is a color change that accompanies this reaction. The dichromate and sulfuric acid, or the chromic acid, is orange, and when it oxidizes the alcohol, we go from chromium 6 to chromium 3, and that gives us a greenish blue color. Okay, this particular reaction was was used in the old breathalyzer sobriety tests. Okay, when a suspect was stopped for possible drunk driving, they would blow into a tube, and if the solution changed from orange to blue-green, that would indicate they had alcohol on their breath. Okay, nowadays, the police use a fuel cell sensor, and it uses oxidant to oxidize the ethanol. Okay, this last point, chromium is highly toxic and difficult to dispose of properly. Okay, so when we do oxidations in the lab, okay, we typically don't prefer to use chromium reagents. Okay, again, because of the toxicity and the expense involved in disposing of them. The big advantage, of course, is there's a color change. You can see that an oxidation is taking place. See, around the year 2000, there was a movie that came out called Erin Brockovich. It was about an environmental activist. And out in California, the utility company was improperly dumping dichromate into the groundwater. And many people were getting poisoned. They were dying of cancer as a result of the dichromate. Okay, so here we have the formation of the chromate ion. Okay, in the presence of sulfuric acid and water, we form two molecules of chromic acid. Chromium trioxide, okay, can also form chromic acid. And in both these cases, chromium has the +6 oxidation state. Okay, so here's the oxidation mechanism. Okay, the alcohol reacts with chromic acid, splits out water. We form this chromate ester. Water then removes this hydrogen. Okay, this pair of electrons shifts, and then chromium breaks off. And we get our ketone in this case, and then chromium 4. We also get chromium 3. Let's see, someone needs to mute. Someone needs to mute.
Like we can get retouch slides instead of printing out all the slides.
Okay. All right, so let's look at primary alcohols next. Primary alcohols can be oxidized to either aldehydes or carboxylic acids, depending on the conditions. Okay, if you use dichromate or chromium trioxide and sulfuric acid, you cannot stop at the aldehyde. Okay, the aldehyde is one of the most easily oxidized groups, and it goes all the way to the carboxylic acid. Okay, so what if we want to stop at the aldehyde? Okay, well, a good option is to use this reagent called PCC. And as long as we avoid water, we typically do this in something like methylene chloride, we can stop at the aldehyde. Okay, it oxidizes primary alcohols to aldehydes. Secondary alcohols go to ketones. Okay, this is the formula for PCC. Okay, this 6-membered ring, it looks like benzene, but one of the carbons is replaced with a nitrogen. That's pyridine. The conjugate acid of that is pyridinium. And then the counter ion is chlorochromate, again, a chromium 6 reagent. Okay, so here's an example. Heptan 1-ol is oxidized to the corresponding aldehyde, heptanal, using PCC and dichloromethane. Okay, tertiary alcohols cannot be oxidized except under really extreme conditions. Okay, and this is because the carbon does not have a hydrogen attached to it. And so oxidation would have to involve breaking a CC bond. Okay, there are various tests that we can use with chromic acid to test for the presence of, or to test for the classification of an alcohol. Okay, so for example, we have an unknown compound. We think it's an alcohol, and other evidence indicates it's an alcohol. And we can apply this chromic acid test. And if it's a tertiary alcohol, it won't change the chromic acid from orange to blue-green. Okay, primary and secondary alcohol will result in a color change. Okay, this is a reaction that we've done in the lab, and with the organic chemistry lab, we've used this to replace dichromate. This is the use of sodium hypochlorite. Sodium hypochlorite is just household bleach. It's about a 5 or 6% solution, and we can oxidize alcohols without heavy metals or generating hazardous waste. Okay, and for example, cyclohexanol, which is a secondary alcohol, is converted to cyclohexanone. And in the laboratory, besides water, we typically use acetic acid as the solvent. Okay, and then the cyclohexanone is removed by extraction. The byproducts are ordinary salt, and if we're using acetic acid, then vinegar. So our byproducts would be salt and vinegar, which are very readily disposed of. Okay, the disadvantage of this is that we don't observe the color change that takes place like with dichromate. Okay, here's another oxidation method. This is called the Swern, and it's a fairly complex mechanism. Okay, we can oxidize primary or secondary alcohols. And in the case of primary alcohols, we can stop at the aldehyde. This uses dimethyl sulfoxide and oxalyl chloride. Okay, I'm going to write the formula here for oxalyl chloride. This is oxalyl chloride. All right, and then okay, the byproducts here are, let's see, we get carbon dioxide, and we get some carbon monoxide and HCl. So it's a pretty complicated mechanism. Okay, another way of oxidizing primary or secondary alcohols is to use this reagent. It's a high valent iodine reagent. It's called the Des-Martin periiodinane, or DMP. Okay, this takes place under mild conditions, room temperature, neutral pH, and it gives really good yields. Okay, so how would you convert cyclopentanol to cyclopentanone? Okay, we could use chromium trioxide, we could use swern, we could use bleach and vinegar like shown here. We could use the DMP. Okay, so we have lots of options. Okay, here we have the conversion of 2-octene-1-ol to 2-octenal. Structure is shown there. Primary alcohol to an aldehyde. And okay, we can use any of these methods. Okay, we do not want to use dichromate or chromium trioxide for two reasons. Okay, not only would the carboxylic acid get oxidized to, not only would the aldehyde get oxidized to a carboxylic acid, the double bond would also get oxidized. It could form a diol, or it could cleave altogether. Right, in the body, the liver produces an enzyme called alcohol dehydrogenase, and that is an enzyme that catalyzes the oxidation of ethanol. The actual oxidizing agent is one that's called nicotinamide adenine dinucleotide, or NAD+. Ethanol gets oxidized to acetaldehyde, then to acetic acid. Acetic acid is a normal metabolite, which is then excreted by the body. Okay, if someone consumes too much alcohol too quickly, or even over an extended period of time, acetaldehyde is what damages the liver. Okay, accordingly, okay, I might also mention methanol is also oxidized under these conditions. It first gets oxidized to formaldehyde, and formaldehyde's a gas. And what happens is that if someone consumes methanol, in addition to digestive disorders and death, methanol can cause blindness, okay, because the formaldehyde damages the retina of the eye. Right, so here's the enzymatic oxidation of ethanol. So it's first converted to acetaldehyde, then acetaldehyde is then converted to acetic acid. Right, so methanol is oxidized to formaldehyde, then to formic acid. Both formaldehyde and formic acid are more toxic than methanol. Formic acid is about 10 times more acidic than acetic acid. It's very corrosive, very irritating. Okay, we'll talk about that next semester, but formic acid is what causes fire ant burns and bee stings to be so painful. Right, ethylene glycol oxidizes, gets oxidized to oxalic acid, again, which is very toxic. Oxalic acid can do a number of things. One is it can form calcium oxalate, which is an insoluble solid, which can plug up your kidneys. And oxalic acid, of course, is toxic in and of itself. Okay, so why do we mention ethylene glycol? Okay, this is a major ingredient in the antifreeze with the green dye. And ethylene glycol, okay, when it leaks out of car radiators onto the pavement, dogs can drink from the puddles of water and get ethylene glycol poisoning, antifreeze poisoning. And the treatment of this is to give the dog an IV which contains ethanol. Turns out that ethanol binds more strongly to the receptors than ethylene glycol does. Okay, there have also been cases of antifreeze poisoning, self-induced or attempted homicide with ethylene glycol. And this is the remedy, is to use ethanol. Right, next we'll look at alcohol as a nucleophile. Okay, alcohols themselves are weak nucleophiles since they're neutral. Alkoxides, which are the conjugate base of alcohols, are strong nucleophiles. Okay, we form a new carbon-oxygen bond, and then we break an OH bond. Okay, this is a reaction we mentioned in the previous chapter. Okay, we can convert an alcohol to an alkoxide using sodium or potassium. And that takes it from a weak nucleophile to a strong nucleophile. Okay, and then once we've got this alkoxide, we can then do an SN2 reaction. Okay, our substrate has to be either primary or methyl, otherwise we get E2 elimination. Okay, this gives us an ether. Okay, the other way that we can do substitution with alcohols is to protonate the hydroxyl group to convert it into a better leaving group, that is water. Okay, OH is a really poor leaving group. Okay, so one way of converting it to a better leaving group, of course, is to protonate it. We've done a couple of labs where we've done that, the T-butyl chloride and the 1-bromobutane. Okay, another way to convert OH into a better leaving group is to transform it into a tosylate ester. Tosylate is a contraction of p-toluene sulfonate. Okay, so this is the formula for p-toluene sulfonic acid. And if we split out water, we make what is called a tosylate ester. This is abbreviated as ROTS. And it turns out the tosylate is an excellent leaving group. We can do both substitution, SN2, and elimination reactions readily with tosylate esters. Tosylate esters are formed using tosyl chloride and pyridine, okay, rather than directly from p-toluene sulfonic acid. So tosyl chloride would have a chlorine here instead of the OH. And so we would split out HCl, and then pyridine is both a solvent and it is a base that neutralizes the HCl. Okay, so here we've got this good leaving group. We can do SN2 or E2 reactions. Okay, so here's one example of an SN2. Okay, so iodide is our nucleophile. It attacks from the backside, kicks out tosylate, and since it is an SN2, inversion occurs. We start out with S2-butyl tosylate, and our product now is R2-butyl iodide. Okay, the reason that tosylate is a good leaving group is it's a weak base because it's resonance stabilized. The anion is resonance stabilized, and we can spread the negative charge among all three of these oxygens. Okay, so it's a particularly stable anion. Okay, here's just a few of the reactions that we can do with tosylate esters. Okay, we can convert tosylate back to an alcohol. Okay, where this might be useful is, okay, if we have the R configuration, we wanted to make the S, this would be a way in which we could readily do that. We can make nitriles, we can make halides, alkoxides, amine salts, and then we can also convert tosylates to alkanes. Okay, we saw lithium aluminum hydride in the previous chapter. That was used to reduce aldehydes, ketones, and esters to alcohols, but it can be used to reduce tosylates to alkanes. Okay, so there's primarily two methods for converting alcohols into alkanes. Okay, one would be to do a dehydration first and then to do a hydrogenation. Okay, we can dehydrate, say with sulfuric acid or phosphoric acid to the alkene and then add hydrogen. Okay, another way would be to make the tosylate and then reduce it with lithium aluminum hydride. Okay, so hydride is the nucleophile that comes in and displaces the tosylate. All right. Like water, alcohols are weak bases. And so they can react with strong acids to form this oxonium ion. And then using a nucleophile, we can do a substitution. Okay, we did both an SN1 and an SN2 with this. We used 1-butanol or butan-1-ol and HBr, and then we used T-butyl alcohol and HCl to make the corresponding halide. Okay, water is a much better leaving group, of course, than hydroxide. Okay, this shows the reaction of cyclohexanol with HBr to form bromocyclohexane. Okay, and again, this is just like we did in the lab. The OH is protonated. Okay, this would probably be SN1. Okay, OH is, I'm sorry, water is a good leaving group. And then tertiary and secondary alcohols would react with the bromide by SN1. Okay, but primary alcohols would have to react by SN2. Okay, this is almost the same reaction we did in lab, except with HBr instead of HCl. Okay, so the tert-butyl alcohol picks up an H. Water leaves, we have heterolysis to give a carbocation, and then bromide forms a covalent bond. Okay, that's an SN1. Okay, and this is the same mechanism that we did in lab with bromobutane. We converted sodium bromide to HBr using sulfuric acid. Okay, so butan 1-ol uses the oxygen to pick up an H, and then bromide attacks from the back, kicks out water, and we get 1-bromobutane. All right, in the reaction of alcohols with, with HCl, chloride is a weaker nucleophile than bromide. Okay, it's small, it's less polarizable. Okay, with the addition of zinc chloride is actually a Lewis acid, that will bind strongly with the oxygen of the OH to promote the reaction. Okay, this gives us another simple chemical test. Okay, so we have conversion of an alcohol to an alkyl chloride under SN1 conditions. Okay, what we observe is we'll observe either a cloudiness or a precipitate that occurs. The alcohol is typically soluble or partially soluble in the HCl. The alkyl chloride is typically not soluble, so it forms either a precipitate or it produces a cloudy mixture. Okay, and since this is SN1, primary alcohols will react slowly or not at all. Secondary alcohols within 1 to 5 minutes, and tertiary alcohols in less than a minute. Okay, so we think we have an alcohol. We can run this test, and it will tell us whether it's primary, secondary, or tertiary. Okay, so here is the reaction with the Lucas reagent. The zinc chloride gives us a better leaving group. So chloride comes in from the back and displaces this leaving group. The SN2 reaction is very slow, and it can take from several minutes to several days. Okay, on the other hand, with a tertiary alcohol, the SN1 occurs very rapidly. Okay, so here's an SN1 with isopropyl alcohol. Okay, instead of chloride displacing this leaving group, the leaving group leaves on its own, and then chloride comes in. Okay, there's a lot of limitations of using hydrogen halides like HCl and HBr. Typically, we have poor yields of alkyl chlorides from primary and secondary alcohols. We can have elimination competing with substitution. We can have carbocation rearrangement. And there is a limited ability to make a number of alkyl halides. Okay, so here's an example of a rearrangement that takes place. All right, so oxygen gets protonated, water leaves, we get a secondary carbocation. Right, then we'll have a hydride shift to give us a tertiary carbocation, which then bromide rapidly attacks. So we get the rearranged product. Okay, so what's the alternative? using HCl or HBr or even HI. One alternative is to use phosphorus halides. Okay, these give really good yields with primary and secondary alcohols. We can use PCl3 to make alkyl chlorides. Thionyl chloride actually works better, but you can still use PCl3. To make alkyl bromides from alcohols, we can use PBr3. And then to convert alcohols into alkyl iodides, one way of doing that is to combine elemental phosphorus and elemental iodine. Okay, these will spontaneously react to form PI3. PI3 is difficult to store. It doesn't have a long shelf life. Okay, so here we have neopentyl alcohol, and we can convert that to the corresponding bromide in 60% yield. Okay, this would be, this reaction wouldn't work very well at all with HCl or HBr because, of course, we would have a methyl shift. Okay, with phosphorus and iodine, we can convert this alcohol to the corresponding iodide in good yield. Okay, cyclopentanol with PBr3 gives us bromocyclopentane. Right, the stoichiometry is 3:1. Since you have 3 bromides, PBr3 can produce 3 moles of, or 3 equivalents of alkyl bromide. Right, here's the mechanism. Right, the alcohol will attack phosphorus and kick out a bromide ion, okay, by an SN2. And this gives us an excellent leaving group. Okay, so bromide comes in from the backside, attacks, and then displaces this leaving group. Okay, and then this can happen 2 more times on the same phosphorus. Okay, it is an SN2, so we'll have inversion of configuration when this happens. Okay, and this overcomes a lot of the disadvantages of using HBr or HCl. We don't have carbocation rearrangement. It's a faster reaction. Okay, if you think back to the bromobutane, we had to reflux that for about an hour. We don't have to worry about side reactions like elimination. All right, thionyl chloride can also be used to convert alcohols to alkyl halides. This is the formula for thionyl chloride. And the byproducts here are sulfur dioxide and HCl, both of which are gases. They can be easily trapped and removed, and that prevents the reaction from going backwards. So you can get alkyl chlorides at very good yields. Okay, so this is how it works. Okay, so sulfur is very electrophilic because it has 3 atoms which are more electronegative than it, the 2 chlorines and the oxygen. Okay, so the alcohol oxygen attacks the sulfur, and then this tetrahedral intermediate then collapses. Oxygen pushes back, kicks out the chloride. Chloride removes this hydrogen. We get what is called a chlorosulfide ester. We then have a dissociation that occurs, and then That gives us this ion pair in which chloride rapidly attacks. Okay, we've done this actual reaction in lab. It's a dehydration. Okay, using sulfuric acid, you can dehydrate cyclohexanol into cyclohexene. There is a carbocation intermediate if we have a secondary or tertiary alcohol. If there's more than one alkene that can be formed, the Zaitsev product is favored, the more substituted alkene. Let's see, we'll talk about bimolecular dehydration later on in the chapter. But bimolecular dehydration is a reaction in which we can form an ether from an alcohol. Okay, so here's the mechanism. Oxygen gets protonated, the water leaves, and then water removes a beta hydrogen. Okay, rearrangements are possible, and primary alcohols especially will rearrange. So this is not a good reaction for converting primary alcohols to alkenes. Okay, so this is the general mechanism for dehydration by E1. Okay, this is the reaction profile. The rate limiting step is the formation of the carbocation, heterolysis, water leaving. And next time we'll look at bimolecular dehydration. So I'm going to go ahead and stop there. Monday's class will be remote. No class on Wednesday. Friday's class will also be remote.